I am Dr. Binu. In second year, fourth semester LIC subject, the second topic in the first unit is basic planar process. It consists of various steps or stages started from silicon wafer preparation. The silicon wafer is here represented as substrate, epitaxial growth, oxidation, photolithography, diffusion, ion implantation, isolation technique, metallization, assembly processing and packaging. The first method is silicon wafer preparation. The silicon wafer preparation consists of following steps. The first one is crystal growth and doping, ingot trimming and grinding, ingot slicing, wafer polishing and etching, wafer cleaning. The different steps used is represented in this diagram. In the silicon wafer preparation, the silicon material used for the crystal growth is 99.999% pure polycrystalline silicon. In order to produce the crystal growth process, Czochralski crystal growth process is mostly used in order to produce the silicon ingots. Here, to provide the silicon ingots, the silicon melting point is 1420 degrees Celsius. The second step is epitaxial growth. Here the epitaxial growth word is from the Greek word. Here epi meaning is upon. Taxion is nothing but arranged. The basic chemical process or reaction used in the epitaxial growth is hydrogen reduction of silicon tetrachloride. Silicon tetrachloride is mixed with the hydrogen, means the hydrogen is combined with the chlorine becomes hydrochloride. Then we will get the pure silicon. The process is normally taking place in 1200 degrees Celsius. The epitaxial growth procedure is represented in this diagram. The third step is oxidation. Oxidation is nothing but in order to prevent the diffusion of silicon, the oxide is mixed with pure silicon, then it becomes SiO2. The important purpose of oxidation is the SiO2 is a hard layer protective coating, so it is unaffected by all the reagents. It can be provided except hydrochloric acid. Then select by means of selective etching of SiO2, diffusion of impurities can be taken place. The chemical reaction used in the oxidation is silicon is combined with either oxygen or hydrogen, which provides SiO2 plus hydrogen. The oxidation used here is thermal oxidation. The temperature used to provide the oxidation is normally 950 degrees Celsius to 1115 degrees Celsius. The amount of the thickness of the film which is coated for the oxidation depends upon the time of oxidation, the temperature used for the oxidation as well as the moisture content. The thickness of the oxide layer is normally in the range of 0.02 mm to 2 mm. The fourth step is photolithography. Photolithography involves two stages, making a photographic mask as well as photo etching. The various steps used in the photolithography is represented in the diagram. The fifth step is diffusion. This is also the important process of fabrication method. Here the high temperature furnace having the flat temperature profile over some 20 cc length is normally used. The quartz board containing 20 cleaned wafer is pushed into the hot zone with a temperature of 1000 degrees Celsius. The impurities used for the diffusion are boron based components are boron oxide and boron chloride, as well as for phosphorus based materials are phosphorus oxychloride and phosphorus pentoxide. How the diffusion is taking place over the substrate is represented in the diagram. The normal duration for the diffusion is 2 hours. The sixth step is ion implantation. Bombarding the substrate with ions accelerated to the high velocity. By means of this operation, ions are implanted. By means of precise control, the amount and distribution of the dosages can be varied. The ion sources may be a gas source or solid source. The process for ion implantation is represented in this diagram. In order to adjust the XY axis, the X as well as Y deflection plates are used. Seventh one is isolation techniques. All the components are fabricated on a single crystal wafer. They must be electrically isolated from each other in order to avoid the short circuit. There are two methods are normally used for isolation of integrated circuits: PN junction isolation and dielectric isolation. The PN junction isolation is represented by means of this diagram. The P type as well as the N type is isolated by means of this method. The second isolation, dielectric isolation. In order to isolate the PN materials, dielectric is used. So this type of isolation is called as dielectric isolation. The eighth step is metallization. The purpose of this process is to produce the thin metal film layer that will serve to make the interconnection to the various components on the chip. Normally, aluminum is used for the metallization in most of the ICs. Why? Because of means the aluminum has more advantages. It is a relatively good conductor, easy to deposit aluminum films using vacuum deposition. Aluminum makes good mechanical bond with silicon. Aluminum forms low resistance, non-rectifying contact with p-type silicon and the heavily doped n-type silicon. The process of metallization is represented in the diagram.